This is video 3 for chapter 12 of Levene. We're continuing to look at the chi-square tests. This is the first portion, still the first portion of the chapter. We're trying to compute expected frequencies for the two hotels whose performance we're trying to compare. Again, for some strange reason, the authors don't directly tell us that to get the expected frequency, you have to multiply the estimate of the population proportion computed earlier by the number of respondents from which the feedback was received in each hotel. So we have to multiply 0.6483 by 227 to get the expected frequency of positive responses, yes, for Beachcomber, and same operation. We have to perform the same operation for Windsurfer. So the p-bar values are based on the assumption that the null hypothesis is correct, and the null states that the proportion for Beachcomber is the same, equals to the proportion of Windsurfer, and that has to do with the proportion of positive and negative responses. If that is true, then the hotels perform similarly when it comes to servicing the guests. If there is a difference, if we reject the null, then one of the hotels is underperforming. Continuing to page 6. Okay, they tell us the table 12.3 represents these expected frequencies next to the corresponding observed frequencies. Okay, here's the table. We have the observed frequencies, which we pulled from the responses of the guests, and the expected frequencies, which we have calculated based on the null hypothesis. Here they stated again, to test the null hypothesis that the population proportions are equal. Once again, we're doing this to see if the difference is so small between the two proportions that it will convince us that the performance of the hotels doesn't differ. So we test the null hypothesis of pi1 equaling pi2 against the alternative that the population proportions are not equal. You use the observed and expected frequencies from table 12.3 to compute the chi-square test statistic given by equation 12.1 on page 464. Let's go back there, 2 pages back. This is what we are after, and we now have all the terms for the numerator, and obviously we have the denominator, which is expected frequencies. We have observed and you use the observed and expected frequencies from table 12.3 to compute chi-square statistic, and here it is. They forgot to tell us. Everything has to be repeated, underscored, and underlined. This is our chi-square statistic. And these are the steps that we are taking to receive it. This can be reproduced in Excel, and we will do it after this portion of the chapter. By the way, I need to properly name this portion of the chapter. We're looking at chi-square test for the difference between two proportions. And the proportions come from independent samples. That's why we have the population Greek letters here. We're comparing two populations by looking at the two hotels. Now that we have the calculation, here are our chi-square values. we're going to have to use the chi-square table to come up with the critical values against which we'll be comparing the calculated values. The chi-square distribution is a right-skewed distribution whose shape depends solely on the number of degrees of freedom, that is, how much they can vary in how many directions. And how many directions the values, calculated values can vary. You find the critical value of chi-square test statistic from table E4, a portion of which is presented right here. Table E4 was on page, let's see which page it was. That was page 796. It's on 796. We have critical values of chi-square. So this table right here is a portion of the same table on page 796. So let's give it some silly color. Let's do this. There. So we know we've looked at it, and highlight what we want. Now this is the critical value for chi-square. As they mentioned, it depends only on the degrees of freedom. And this is the degrees of freedom here because we have only two populations. Okay. The table itself states, for a particular number of degrees of freedom, entry represents the critical value of chi-squared corresponding to a specified upper tail area, alpha, which is 0.05 for us right here. 0.05. Okay. That's about it for the table. The values in table 12.5, which is this, refer to selected upper tail areas of the chi-square distribution. Okay. As usual, they don't elaborate on whatever they say. And this is the selected area right here. This is critical value, we just looked it up. The selected area of rejection is this. So that's where we're going to operate. Let's see where we land. Okay. We have the contingency table, the 2x2. A 2x2 contingency table has 2 minus 1 times 2 minus 1, 1 degree of freedom. We had two populations and two types of responses. That's what I didn't mention a second ago. Yes and no responses. Using alpha 0.05 with 1 degree of freedom, the critical value of chi-square from table 12.5 is 3.841. You reject the null if the computed chi-square statistic is greater than 3.841. If the computed statistic is greater than the critical value, obviously it will land, the computed value will land in the rejection region. Now the computed value was 9.05. Let's highlight it here. And this is the sum of these values. Okay, because 9.05 is greater than 3.841, so it's way to the right of the critical value. You reject the null. You conclude that there is a difference in the proportion of guests who would return to the beachcomber and the windsurfer. Well, once again, this is the critical value, and it's 3. All right. So if we're using 9, 9 goes all the way over here. Oh, here's something for us to reproduce, so that'll require a separate video. Let's read this comment. Regions of rejection and non-rejection when finding the chi-square critical value with 1 degree of freedom at 0.05 level of significance. Okay, now this is done in one of the spreadsheets, that they supplied. This can also be done in PHStat, but it's all manual operation. All these entries are manual entries. We'll have to do it in video once we're done reading this. Okay, see section E12.1, we'll do this. To create this, okay. This worksheet includes the expected frequencies, chi-square test statistic, degrees. Okay, let's do the expected frequencies right here. Oops. Expected frequencies, chi-square test statistic right here. It was not OCR'd. Anyway, this is our chi-square test statistic. Degrees of freedom and the p-value. P-value and degrees of freedom right here. Let's make it a little larger so we can see it easier. Okay. This worksheet includes, I need this. That's strange. This worksheet includes the expected frequencies, right here, expected frequencies, chi-square test statistic, right here, degrees of freedom, over here, and p-value, right here. The chi-square test statistic is 9.526, which is greater than the critical value of 3.8415, or the p-value is 0.0026, which is less than 0.05. So you reject the null hypothesis that there is no difference in guest satisfaction between the two hotels. The p-value of 0.0026 is the probability of observing sample proportions as different as or more different than the actual difference. And the actual difference is 0.013 observed in the sample data, 0.013. If the population proportions for the Beachcomber and Windsurfer hotels are equal. Thus, there is strong evidence to conclude that the two hotels are significantly different with respect to guest satisfaction, or with respect to creating the perception of guest satisfaction. So there's going to be something done about that. Okay, as measured by whether the guest is likely to return to the hotel again. An examination of table 12.3 on page 466 indicates what? Indicates that a greater proportion of guests at the Beachcomber are likely to return than at the Windsurfer. Let's go to 466 real quick. Okay. We should have the proportions. I don't think. $163, $147, $154, 169. So greater observed and expected or lower. And here expectation was higher than the observation. So they conclude that this is true. Meaning this is significant. The difference is significant. For the chi-square test to give accurate results for a 2 by 2 table, you must assume that each expected frequency is at least 5. If this assumption is not satisfied, you can use alternative procedures such as Fisher's exact test. Okay, let's stop here and start our next video on page 468.